Hey everyone, so this is going to be video one, I hope, of three short videos, maybe around 10 or 12 minutes each. All right. So where we left off, just a brief discussion of thermodynamics. I know it sounds like a big technical word, but it really is not that complex. So first law of thermodynamics is simply put, energy is conserved. Okay, so energy is conserved. And so essentially what that means is that in all these energy inputs, outputs that we talk about, or transformations, so looking up top here in terms of if I put 100 joules of kinetic energy into my bike to get it to the top of the hill, then here I would have 100 joules of potential energy. Energy in equals energy out. Okay, now we're going to talk about this in a second because what we need to understand is energy can be lost in the form of heat. Okay, so I could, in the process of getting myself up, maybe lose 40 joules of energy to thermal energy, which would leave me with, at the top of this, only 60 joules of energy. But the end result is still I have 100 joules of energy in, and 40 plus 60 gives me a total of 100 joules of energy out. The problem is this energy becomes sort of useless, okay? And that's another thing we'll talk about in a second. Long and short, first law, energy is conserved, all right? Second law of thermodynamics says that in any given system, okay, and again, so in all of this, we're talking about systems, right? And a system could be a collection of matter, or it is a collection of matter. It could be a cup of tea, could be an engine in a car, a cell in your body, your room, all right? We consider a system to be any collection of matter, all right? So in the second law, for any given system, right, all systems tend towards a state of what we call maximum entropy. Okay, now this is another fancy word, but really what it means is disorder or randomness. Okay, so in any given system, there's a tendency to proceed towards a state of disorder. Think about your house, you think about your bedroom, on any given day, during any given week, or your house. You might tidy everything up, you clean up your house, around here, Sundays are cleanup day, clean everything up, it's all nice and ordered, right? It took energy to get it into this state of order. Throughout the rest of the week, we're going to tend towards a state of disorder as, we make breakfast, pile up laundry, make a mess in the bathroom. There's this tendency towards disorder. You throw your clothes on the floor, you got cookie crumbs on the floor. And in order to get it back to that organized state, we have to invest some energy to get it back to order. So there's a natural tendency to disorder. So when we apply this to chemical reactions, a couple of things. So a perfect example is cellular respiration, which we're going to go into detail in chapter 6. But cellular respiration, so we got a chemical reaction in which we have, and I'm going to slide this up a bit, sorry. 1 second, I might not be able to slide that up. Okay, so if we consider our chemical reaction here of cellular respiration, we have some chemical energy that exists in our glucose. So there's chemical energy here in our reactants, and we are going to convert it into these products of carbon dioxide and water, and we are going to convert the chemical energy in this glucose into chemical energy of ATP. Now, we are going from chemical energy to chemical energy, but it is in a different form. The point is that there's an energy transformation, and in that process, we might lose some energy in the form of heat, some thermal energy. Goes back to the same thing I said before. If we had 100 joules of energy available in the bonds of glucose, then we're going to get 100 joules of energy out. Now, we might only get 40 joules of energy in ATP, and the remaining 60 joules is lost as thermal energy. But the point is, energy is conserved. 100 joules of energy in, we get 60 joules of energy out. But unfortunately, for most biological systems, this thermal energy is useless energy. So we tend to say energy is lost, but really, remember, energy is conserved. It's just converted into forms that are less useful, right? Okay, so let's apply these concepts of energy and concepts of thermodynamics to chemical reactions. In the world of chemical reactions, and that's not just biological systems and your cells, but in industry and manufacturing and chemical reactions that take place in nature, there are essentially two types of chemical reactions. We refer to them as endergonic, okay, or you may have heard the term endothermic. So think about that term thermic in terms of energy. So endergonic is a chemical reaction in which energy must be put into the system, must be put into the system. Now, again, remember, in any transformation, right, there's going to be energy invested and energy coming out. In an endergonic reaction, there is a net input of energy, okay? It's not to say we're not going to get energy out, but there's a net input of energy. And so if you can look at the reaction over here, okay, on this axis on the left-hand side here is a measure of potential energy. So what it's saying here is that these reactants have a certain amount of potential energy. And remember, that potential energy is in their bonds, right? So when we say these reactants have a certain amount of potential energy, it's the nature of the atoms that are joined together and the potential energy that exists, like I was talking about yesterday or earlier today, I guess, in terms of the potential energy that exists in the bonds between the atoms. And that will vary depending on the types of atoms, the nature of the bond, etc. In order to get these reactants to form these products, what we're saying is there has to be a net input of energy. So kind of think about going up the slide, right? To make this reaction happen, we actually have to have a net investment of energy, okay? The second type of reaction is what we refer to as exergonic or exothermic. And in these chemical reactions, there is a net output or a net production of energy, a net output of energy. Energy is given off from the system. Energy is given off from the system. Now I said, remember, a system can be any collection of matter. So in this case, our system is the chemicals that are reacting. Here, these reactants have a certain amount of potential energy, and the potential energy that these reactants have is much greater than the potential energy that, if we read across, that these products have. So these things may have been starting with 100 joules of energy, all right? And these products may have only 40 joules of energy. That means that 60 joules of energy has gone into the system. Now, that 60 joules of energy could be lost as thermal energy, which we'll never see again, but some of that that's been given off could be used to drive the work involved or drive the chemical processes taking place in the cell. All right, so those are the two main types of chemical reactions, and we're going to look at these collectively in the process of cellular metabolism. Okay, so as it says, cellular metabolism represents the collective billions of endergonic and exergonic chemical reactions going on in every single cell of your body, right? Many reactions in your body are not a single reaction, but they're a series of reactions coupled together. That means that there's very few things in your body where substance A becomes substance B, and that's it. It's all done. It's usually a series of steps, and we'll kind of understand why. A lot of it has to do with the complex nature of chemical reactions, that they just don't occur in a single step. So it's more like A is converted into B, which is converted into C, and finally D is produced, and D might be the product that your cell needs. What we refer to this as, or we call this a metabolic pathway. All right. And so recognizing that chemical reactions are often a series of steps, could be 4 steps, 5 steps, 10 steps. In chapter 6, we're going to look at cellular respiration. And cellular respiration probably has, I mean, there's probably around 10 or 12 chemical reaction, 10 steps in glycolysis, maybe 8 or 9 steps in the Krebs cycle, and probably 6 or so in the electron transport chain. So here you've got one chemical reaction that you've learned maybe from grade school, but it's really over 20 different chemical reactions representing a metabolic pathway. And some of those chemical reactions may be endergonic, requiring an input of energy, and others might be exergonic, giving off energy.